Chapter 9, Problem 3. A tower crane must always be carefully placed so that there is no net torque tending to tip it. A particular crane at a building site is about to lift a 2,800 kilogram air conditioning unit. The crane's dimensions are shown in the figure in the book, in figure 948b. Part A, where must this crane's 9,500 kilogram counterweight be placed when the load is lifted from the ground? The counterweight is usually moved automatically via sensors and motors to precisely compensate for the load. In part B, determine the maximum load that can be lifted with this counterweight when it is placed at its full extent. Ignore the mass of the beam. Okay, so for part A, well, there's a lot of forces going on in this picture. So definitely gravity pulling on all the masses. We have to take that into account. And they're acting at distances, so that means that those forces due to gravity acting at those distances are going to cause torques. And then we also have to consider the force that the pole itself at the center holding this whole crane up causes on a pivot point. So essentially, we're going to need a free body diagram to do this. In most of these problems in Chapter 9, we're going to need free body diagrams. So here we go. So if we draw like a small crane type thing here, let's say that it's more towards the left. That's not very straight. More towards the left. Okay, it's not straight, but just bear with me. It's supposed both of those lines are supposed to be straight. So we're going to call that our pivot point. Let's do this. So let's say our pivot point's right here. So there's going to be a force due to that pivot point, like I said earlier, from the pole, or a force due to the pole, but it's pivot point pole. It's just essentially the same there. We're going to have a counterweight that we want to include. That's going to have some force associated with it, with a big M. That's going to be the counterweight. It's going to act at a certain distance. Let's call it X. Another force at another distance at the end of here. This is going to be our crane that's going to be picking up what we need. It's going to be our small mass G. So we're going to have force vector, force vector, force vector. Okay. This is going to be acting at a distance D. And now that we have our free body diagram, we can take advantage of Newton's second law, which tells us that the sum of the torques is equal to the moment of inertia multiplied by the angular acceleration. This is really equal to 0, though. So the sum of the torques, in this case, what we should do first is define a direction as positive and negative. So let's say in most cases, counterclockwise ends up being the positive and clockwise ends up being the negative. So let's just take that. Let's take that. This is counterclockwise is this way, clockwise is this way, right? So anything moving towards the left side, kind of like from the right to the left, is going to be positive. From the left to the right is negative. And in that case, that means that mg here is going to be positive, right? Because it's going anti-clockwise. Let's back up off of those. Okay. Now we can do our sum of the torques. The reason we can say this is 0, right, is because it's in equilibrium. So we want to see the free body diagram, calculate the torques about the pivot point labeled in the diagram. The upward force at the pivot will not have any torque, obviously. It's not going to the left or right. The total torque is 0 since the crane is in equilibrium. And that essentially lets us say the sum of the torques is 0. And now we can include the torques. This is going positive, this is going negative. When I say this and that, I'm this and this, right? These are the two forces that have to do with the torques. So let's just get right into it. It's going to be mg, and we just want to multiply by the distance it acts at. It's just x, right? Very easy. So mg here, acting at what distance? D, right? So mgd. And now, since this is equal to x, we just need to do algebra to find, or sorry, I said x, I meant 0. This is equal to 0, so we just need to do algebra to find out what x is, right? Because it actually turns out that we know D. So if we have mgx on the left side, or mgx on the right side, would be equal to mgd on the left side if we added mgd to both sides. And if we wanted to find x, well then the g's would cancel if we divided both sides by g, and then if we divided m, we'll get m over big M times d. So it's essentially a ratio of the masses multiplied by the length from the pivot all the way to the crane. Yeah, this 7.7 meters is in the figure B. D is going to be 7.7 meters, but we're not exactly sure where to put it yet. That's why we chose X for this one. So that can change at any time, right? So X in that case, in the case of A, where must the crane's counterweight be placed so that when the load is lifted from the ground? The answer is that it should be placed 2.3 meters at 2.3 meters. But we know that the original distance between these from figure B says that it's 3.4 meters, right? The total distance is 3.4 meters. So that means basically it's going to have to be like a meter from the edge, essentially, about a meter from the edge, right? That's where you want to put the counterweight so that it balances out. And then part B, let's go back. Determine the maximum load that can be lifted with this counterweight when it is placed at its full extent. So what does that mean? This means now that we're looking for a maximum mass possible. We're looking for the maximum mass that basically we're instead of making we were given all these numbers in part B, in the part B figure, 3.4, 7.7, and 2800. 7.7 stayed as the control, but 3.4 we switched to X to find that we basically made 3.4 a variable to find a certain number for 9500. And so now we're just switching that around. Instead of making the distance a variable at the top, we're going to make the mass a variable at the bottom. So we're not going to use 2800 kilograms anymore. Now we're going to use 9500 kilograms. So let's try that out. So same idea, sum of the torques is equal to 0. But before I say it's equal to 0, let's say what it actually is, right? So we have the counterweight force multiplied by the counterweight max distance, because we're talking about full distance now, minus the force due to the minus the force of the original weight times the distance it's at, and that is all equal to 0. With that being the case, we know everything except for little m max. So little m max GD is equal to big M G X max. So m max is equal to mg x max over GD. So the g's cancel like they did before, and we have big M times x max, which is just 3.4, right? It's just what we didn't use before. But big M is 9500, which it was 2800 before. It's 9500, sorry. So we have 9500. These are canceled, multiplied by 3.4 divided by 7.7. This gives us a mass of 4,200 kilograms. So if we were wondering, we just want to sum the torques about the pivot point. Mass, the little m is the unknown mass in this case, and the counterweight is at its maximum distance, is why we use 3.4 for x max. Yeah, and so the maximum load that this crane could carry if the counterweight was at the full distance is about 4 tons, 4,200 kilograms.